Guys, great to be here. Thank you for having me. Really appreciate it. Special thing for me, as I used to live a 5-minute walk from here as a Stanford undergrad. So a lot of fun to be back. And of course, the conference is a little bit cooler at Slack. So I could say, wow, I gave a talk at Slack. But this is awesome. For the physicists in the room, I actually started out as a math student and did a PhD in math in an area inspired by gauge theory, where you study sort of curvature heat flows of PDEs and then correlate them with the existence of algebraic structures like stable vector bundles. So that was a lot of fun, but feels like a really long time ago now. There's no data like more data is a phrase that I learned in the speech recognition community, and I'll tell you a little bit about what happened after the math work. And it refers to the fact that when you're doing acoustic modeling and language modeling, you put in more data and your models get better. And at the beginning of sort of the HMM phase of speech recognition, it was all about the fancy algorithms, and then over time it became all about the extra data. And so a lot of this talk is sort of taking some of those ideas and kind of taking this phrase as a guide through big data analytics. And it's kind of a tough thing to follow my carry here, but I'll give some of my answers to his questions. And of course, I'll give them all in black and white, and hopefully that'll make it a lot easier to kind of see where I'm coming from and where things stand. So here's the first one. That's my license plate. So, after building speech recognition models, worked on SQL Server for a while, did fuzzy joins and fuzzy grouping with actually some folks who are here today, and then moved on to Google, worked on ads for a while where you deal with a lot of large-scale data, worked on search for a while, and then ultimately ended up working in data infrastructure, because those are the things that, frankly, in order to speed up what you're doing, you just need better data infrastructure for all those things. And so, the Dremel team started out with engineers, actually one engineer saying, MapReduce and Sawzall and all these things, really great, but why is it all so slow? And then grew from there. So Andrei Gubarev, started the effort, and then other folks joined. So Sergey Melnik, that some of you know from the community, joined and added some database thinking into it. And over time, the system started with three basic systems ideas, and I won't bore you with all the system stuff, but number one, aggregation trees. So if you're going to have thousands of servers and maybe 100,000 cores participating in something, you probably don't want to have master-slave architecture. So that was a big one. Number two, you really need to address protocol buffers or JSON-style data, something with structure if you're going to do useful stuff with not just more traditional databases, but also like HTML documents and things of that nature. And then I think one of the big third ideas was just how do you then weave that in a way that people can actually use? And so we made up a SQL-like language. And it seemed like a good idea at the time. Well, people love making up languages at Google, and so I loved it too. In retrospect, that was a great choice for a lot of the applications inside of the company, but then made it hard to take the next steps, which were around like, how do the finance team use this, and how does the HR team use this, and that built into the kind of the later iterations, which eventually got to Tenzing. How do I do ETL with this, because I really want to actually bring the data in and all that good stuff. So I think the story of these systems is kind of a roll-up of you start with some basic ideas, you build the system, you see what people do with it, and then you try to evolve it, and this is the, if you like, the limit of that evolution. So let me go back to this sort of there's no data like more data idea, just by diving into some examples of, wow, there really is more data in this example. So this is from a really interesting example from an actual utility company, and I honestly didn't think of utility companies as the fount of a ton of new data, but actually they really are. So utility companies manage tens of thousands of miles of, for example, gas pipe. Okay, so tens of thousands of miles of gas pipe laid over centuries, maybe one or two, and then completely different gas pipes, completely different sizes, locations, all of these good things. But here's this organization that's trying to manage them and honestly keep us all safe, which is a hard problem. And so they've started to look at how do I tell, whether this gas pipe needs me to do something to it, like replace it or fix it up or whatever. And so they do all kinds of things. They send guys who dig up the gas pipes, and they have special 3D cameras that take 3D models of the gas pipes from the outside and then analyze those. They have robot cars, okay, that drive through live gas pipes and collect, infrared and sonar and video and whatever else, right, to try to measure the gas pipe, and just amazing things. And not only that, but it's done by consortia of utility companies that work together. And so there's no data like more data, but some of it ends up on laptops, some of it ends up in cloud systems, some of it ends up on the cars. And they really just need to pull it together to make a good picture and say, what is the next generation of algorithms going to look like that analyzes all these gas pipes, and how do we do it all safely, because we're a highly regulated type of industry, and people object if we get some of the algorithms wrong. So what do we do? So hold that thought. Let me give you a different example. So e-commerce. By now, e-commerce feels kind of old. It's like, oh yeah, of course I do all my shopping on Amazon, but here's an example of an e-commerce company that, I'm sure you guys all know, but they do a bunch of analysis of all the orders that they get. And it's not as sort of extreme as the, oh, look, robot cars through pipes, but a lot of the stuff they're doing is looking at, okay, well, what do people do on my site? And then how do I go back and figure out where I'm spending the money in my marketing that helps those people find the things that they want more efficiently. And even these problems are not fully solved, and part of the reason is because if you just look at the purchase data, which is what you're looking at right here, it's hard to tell what was the last thing that you did and how does it lead to the purchase that you made. And then when you start to think about what you need to actually understand that, you have to say, well, I need to look at all the behavior of the user before they made that last purchase. And all of a sudden, you're looking at 100x and many billions of events. And also a path through these events that, again, multiplies the space. And so, some of the things that these folks are finding is that algorithm speed up, in theory, it's straightforward, but often they're kind of frustrated by the fact that, they've used a lot of different things along the path to actually figure out how to do each step. And then when you go to co-optimize the whole thing, it's really, really a tough exercise in optimization. And so here's what we've been calling the canonical data supply chain, and kind of gets at this idea of there's no data like more data. Whatever you're doing, the next round of analysis, and I'm really talking about analytical systems, not kind of the completely general, big data management systems that we've been chatting about, because I frankly think that whole answer of how do we put it all together isn't known. I think that's a research problem, and so I'm glad somebody's working on it with partly my tax dollars as well. But having worked on the Spanner team, for example, briefly at Google, I just felt like at some point it's really, really tough to kind of answer all the questions together, and I think that there is now tech that can sort of move the analytical part of this story a little further along. And so what you see here is we've sort of mapped out the sort of gold standards of how people do the stages of their data supply chain. And I use this broader term data supply chain because more and more it's not just about the data that's in your own organization, but as well as the organizations that feed your organization and the organizations that you feed data into. So for example, I was just talking to Jessie from Lawrence Livermore Labs, and she collects seismology data, but that comes from a bunch of organizations. She then feeds it into other organizations, and that's really the typical case. It happens in commerce, it happens in every environment. And so how you think about this sort of gather, ETL step, and then the analysis, and then the sharing has sort of been, over the years, segmented into a bunch of super successful, really, really powerful products, but it's also led to an environment where it's kind of tough. You have to end up putting them together. There's usually experts at every stage, and it takes a while to kind of get your answer out. And so what has changed? It has been thus for a while. In fact, I would say in every iteration, the data warehousing folks won in this question, right? It's like, okay, well, what do? You put it all in one place, whatever the place ends up being. Then you use the place to answer the question, and then you go from there. So I think, first of all, what's changed is, number one, the compute power has just been widely dispersed. I mean, I have probably more compute on me right now than some EDWs must have in the early days. And so there's just a ton of more processing, both on the edge, as well as in your laptops and in the various computers in the enterprise. The distributed systems to use that compute have gotten hugely better, and that's partly as the work from the Googles, the Facebooks, the Amazons, the Yahoos, and all of these folks. I think that people have just seen the value of analysis, and I mean in dollar terms, in such a big way from kind of the first wave of internet companies, that I will wager that the bulk of compute back in the day was primarily LTP with a few people doing a little bit of OLAP analysis, whereas today I'll bet you that in most environments, and just judging from the growth of Dremel at Google, people are doing a huge amount of analysis on any piece of data that they gather, because they know, right, that the competition has moved to the edge, and so the more of a step that you can take at every time, the better off you are, and it's worth the compute. The third big element is just network. It used to be really, really hard to move a terabyte, and you can now move a terabyte off of the switch that you buy at Costco, not Fry's. And in general, in every data center, and in fact inside of Google, right, there's just a lot more ability to move bits. And that was in fact one of the big turning points for Dremel, which started out as a system where you brought all the data local and then queried, and eventually became a pure analysis system where we read the data wherever it was. And that would not have been possible without the networking as it is today. And I think that's evolving even further with software-defined networking and a lot of these elements. So you see a bunch of charts like this about how much networking can you have. And I think the reality is basically that you can have enough networking now for cheap or free that you can write your applications differently. And so I think that that's a big predicate. I think another big element here is just that the odds are higher, or the stakes are higher, I should say. Privacy, compliance, all of these things have just become such central elements of how you use the data. A data breach causes a whole organization to change its structure. There are many more laws now that protect kind of the boundaries and so on and so forth. And so how you think about the analysis and how you operate in the analysis starts to force you to kind of change the structure of the systems. And then of course, right, people are spending more money, right? And so as people spend more money, more of these systems change. And so this is the question that we get from CIOs the most. So when we say, hey, we've got this awesome analysis system at Metanautix, and by the way, I'm trying really hard not to make this an ad for Metanautix, but rather tell you how we think about the problem. That's the question they ask. They say, any one problem with my data, I can fix it. I do it myself. I hire Accenture. I know there are a lot of Accenture folks here today. Tell me, how do I set it up so that I can handle all the problems in the analysis stack in the future? And so I've got all the data types. I've got all the data shapes. I've got and flat relational data. I've got nested relational. I've got videos. I've got logs. I've got it on file systems. I've got it on NoSQL systems. I've got it in SAS. I've got it all. What do I do? Right? Because ultimately, I want the people on the far right to be able to do whatever they do in the analysis stack, be it with Tableau, be it with spreadsheets, be it with fancy code or whatever. So we've tried to boil it down, and I'm sure you've seen many of these structures, but what we're trying to get at is whatever you're going to do, you better be able to do it fast, not just fast computationally fast, but fast organizationally fast. You better know what you did after you've done it, so the visibility part. And you got to do it in a general way because there are more and more people in your organization that are engaging with data, right? It used to be that primarily your data analysts were engaging with your data, except that now more and more people are called on to be kind of, quote, analysts in the org. And so here's part of our view and our model. I think we're sort of enamored with doing custom stuff. And by custom, I mean at various levels, either writing completely custom systems, and honestly, at some stage, that made sense, right? There was no other set of things that Google could have used at that time, to build their structures. But with all the systems that we've talked about evolving, I think it's becoming much more possible to take off-the-shelf components. But it's not just components, right? So I think one of the things that we see very often is that groups like to write code and like to, for example, integrate at the API level. And that's great, right? I mean, versus not having APIs, integrating at the API level is great. But once you bake in an API, that's a marriage, right? I think if you have to go and rip out an API that you depend on for whatever, the robot car, then it's a very deep binding. And so integrating at the data level, integrating at the schema level, integrating at even ODBC, right, I would say is a much better choice because the data is going to change, but the APIs are going to change even faster in a lot of these systems. So custom to standard, I think, is a big one. Imperative to declarative is another big one. I mean, I think, again, because often our bias is towards writing code, we end up with a lot of it, and imperative programming is great, right? You can generally beat the machine if you really have to. But when you end up running your system in and robot cars and cell phones and massive data centers and laptops and all of these things, it's really, really tough to do it in an imperative manner. And so this is, again, one of the parts where I think it's important to remember I'm talking about analytics here. Because obviously, right, writing declarative logic for everything is tough, but I think especially in analytics, it really lends itself to declarative thinking and saying what your intent is rather than saying, how to do it. And, that was actually one of the big ones at Google, I should say, where, SQL is not a perfect language. I think no one would argue that, but it's one of the ones that people know, and it's really easy to translate into other things. So the fact that people know it, right, means you can deploy it to a bunch of your organization, and if what you're looking for is impact and change in what you're doing, well then, using things that people already know and that their apps already use is a big deal. And then secondly, if you decide that you want to have Flume Java underneath, or if you want to have C++ underneath, or if you want to have LLVM, generate JIT underneath, then you still can. Whereas if you've written a low-level imperative program, even if you think of it as a high-level imperative program, then it's really, really hard to go back to this. And so finally, I think the one choice, and this gets back to the sort of cloud versus on-prem versus how do I deploy, I think you're going to deploy hybrid, right? You're going to deploy hybrid whether you like it or not, right? Because your partners have made independent choices from you, because your downstream consumers have made independent choices from you. And so as a result, saying, hey, I'm going to do it only one way is really not practical except for, very small scale. Right, so I think those are some of the big dimensions. And so how we think of this is that you need to simplify the data supply chain for analysis, and I want to hasten to say that this isn't intended to say we should replace the old data supply chain, but rather to say we should look for things that allow us to get end-to-end in the data supply chain. And so this concept of a data compute engine I think is useful in that regard because, for example, if you're doing large-scale machine learning, you're doing iteration after iteration. If you're doing feature engineering, as we heard about from PayPal, or if you're doing debugging, or if you're doing whatever you're doing, right, you're going through that cycle again and again. And the faster you can go through that cycle end to end, the quicker you find the answer. And so if the system supports you in that regard and uses kind of a general language, and I think, again, thinking about the Wolfram example of saying, the language separates you from the system. I think that that's critical. The only thing that I would disagree with is if the language is standard, if it's general, and if it's well accepted already, well then that makes the flywheel turn even faster. So I'll mention a couple of things here also. You see that the data compute engine doesn't span the storage and doesn't span the visual analysis. And I think that that's a big deal. I think in many ways, in many organizations, the storage is spoken for. So if you've got a certain class of applications built on MySQL, you can migrate them. I mean, Google did migrate AdWords off of MySQL. It can happen. It's really hard. And if you really want to do that, you can, right? But often, it doesn't necessarily make sense. Yet, you want to be able to combine that data with other data that's in Salesforce or that's in somewhere else. And so separating that storage question, I think, is a big deal, especially for getting adoption. To be able to say, I want to be able to do analysis in a new way in this org. Step one, change your storage. That's a very tough sell. I would make the same point on the far end, visual analysis. And people love whatever visual analytical application they use, be it their own custom front end, be it Excel, be it Tableau, be it something else. Most people use all of these. Certainly Google used and Excel and MicroStrategy and Tableau and Hyperion and ClickTech and the system that I ran. And the decisions that go into that aren't fully rational decisions. They're organizational decisions. And so changing them is not about making the analysis cycle faster, right? And so that's why those two ends are separate from that data compute engine concept. Now, on the other hand, I think the data compute engine can start to eat into elements of the database. And this is about unbundling the traditional RDBMS, right? The traditional RDBMS has its storage manager in it, has this concept that the data's mine, and therefore I can index it well, and I can do all of those clever things. But if you start to pull that out and say, I can't take the data. I can't take the data, but somebody else has it. They're a silo that we're a center of excellence in their org, and they should stay that way for reasons that are completely external to our data management story. But yet I need to run fast queries. What do I do? Well, yes, I can fall back to just scans, but I can start to say, well, I've got a lot of spare CPU, and actually I've got a lot of spare storage. So what if I use some of that CPU to, for example, reshuffle the data different ways? Or if I have multiple replicas of the data, what if I write the different replicas, shuffled in different directions? Those are all various tricks that are kind of part of the trade, and happy to talk through all the details. So I think this unbundling can lead to lots of different kinds of systems. That's actually one of the most important experiences that I would say I had at Google, where I would see a component that somebody wrote, and I'd say, why didn't you just use MySQL for that? But if they unbundled it, they could scale it the way that they wanted to scale it and pay only for the part that they wanted to pay for, right? And I think that ultimately it comes down to a lot of the economics. So I've tried to summarize some of these things in, let's say, as a memorable and perhaps offensive way as possible. So I go back to SQL. SQL illiteracy considered harmful. So a lot of folks say, SQL is really old. I don't like SQL. And frankly, to me, like I don't like set theory. I don't like Venn diagrams. And SQL is a simple language. It has all kinds of hairy parts. But fundamentally, right, it says what, the customer name and so on, from where, right, the specific table, and which part of it you want. So I think being able to write a consistent statement and about what data computation you want to compute, you want to produce, I think is an important thing, is part of literacy with data. I think the other element is, again, back to the distributed systems world. If you write in a declarative manner, then the systems can help you, because our programming languages colleagues can only do so much if we write even Go, right, or even Java, right? It's very, very tough to separate the I/O and to separate the pure computation from all of that data flow. And so I think, if you were starting out in computer languages today, I would ask you, make another really great declarative language and get it adopted in some way, because in the meantime, I think this is the natural option. By the way, right, I think over the years, SQL has been extended in a number of standard ways where you can actually address, with arrays, with nested subqueries and all of these good things, all of the wide variety of data sets that people use today, right? So that's one big one. Binding compute to storage. So I think you've heard this from others, and so I won't belabor this point, but your data will outlive all your storage systems. And this happened at Google in kind of a rapid iteration cycle, where it was like, well, it's still that protocol buffer that we're evolving, and it's still web session or ad sessions or whatever, but we've thrown away GFS and now it's onto Colossus, or we've moved it off of Colossus onto Spanner, or we've moved it off Spanner to Megastore, or we moved it off of Megastore to something else. And so binding your compute to your storage, again, comes from this bundled story of the RDBMS, which is an amazing story, right? Like if you think about what the RDBMS can do, it's a computer, right? But I think that the storage systems are evolving so quickly that I think separating that compute makes a lot of sense. It gets back to the fact that you have enough networking to do it. It gets back to the fact that if you can declaratively say what you're computing, well then it doesn't actually matter what's underneath, and I think that's where the path is going. So rule-based workflows. Ultimately, whatever you're computing, there's going to be parts. And the parts come in recipes that do not age well. They're complicated. And we added this after this happened, and so on. And then it becomes really hard to reason about dependencies. And so, for example, I, at some point, ended up owning the billing data warehouse for Google. Every company that Google buys, right, you end up integrating their billing practices. It's really tough, right, because if people have written script for that, you pretty much have to read the script. You can't recompute dynamically because you don't know what later part is going to depend on what earlier part. And so there's a lot of workflow work out there. I'm sure every one of you has used many workflow systems. The only thing I would say about them is The best workflow systems are the ones that you can't see what the parts are, right? Like if every step of it is executable so that you would say, I would run this step like this, and refers to all the other parts, then that's the best kind of workflow system. So DSLs often in this space sound good, but they're very, very hard to maintain, to be frank. And so being able to analyze that flow of data also gets at all of those issues of security, role-based access, all of these good things. So if your workflow ends up looking like that, then reasoning about it is really, really tough. And certainly versioning it is really, really tough. And so again, that rolls up into how can I make it all declarative? Sometimes people think of declarative as, oh, okay, SQL, more SQL, more SQL. And so I want to leave you with some things that are SQL but not SQL. So this is an image of a fox. It's called a mosaic. A mosaic is an image where you replace every pixel with another image where the colors are picked to be close. Okay, so this is you see the fox there, and then you see the image between the eyes of the fox. And so this JPEG was computed with a single SQL statement using our system. And part of the reason is not because we think you all want to go out and compute mosaics, but partly to say, you should be able to do very broad class of computation. This is a computation that most people would think, oh yeah, I should write some code, it's relatively straightforward. But it's a very simple join. And that same thinking can then start to evolve and say, oh, okay, well, if I can do mosaics, and I can combine photos. So here's a photo that we mosaic into another photo, but then we also do a background. And so that's, again, a single SQL statement. And here's a mosaic that's not just a mosaic of images, but it's a mosaic of videos. We took 4 videos. We then did a mosaic at each frame where we put each of the frames on the corner of it. And then we constructed this new video, which is, again, output from the system. So inputs and outputs should be independent of the actual processing. The system itself shouldn't care if it's reading from a file system or if it's reading from a SQL system or whatever it is. In fact, it shouldn't care where it's reading from. This is a mosaic of a video of our SQL car, where we're reading from the sensors of the SQL car and plotting the position of the SQL car in Tableau, and then constructing that video to see it. So you can really do a lot with declarative processing. Would love to chat more. Almost out of time, so thank you.